Now we have the equation of motion of the magnetization under the macromagnetic approximation. This equation of motion is composed of two terms. A precession term that accounts for the precession of the magnetization around the effective field, and a damping term that relaxes the magnetic energy and accounts for the progressive alignment of the magnetization towards its rest position. In this part, we are going to see how the competition between these two terms lead to magnetization switching and magnetic resonance. Let's move on. Let's look at the magnetization reversal first. In this example, we are going to consider a small magnetic particle with uniaxial anisotropy. Because this particle is assumed to be very small, the magnetization is homogeneous and behaves like a macrospin. This is called the Stoner-Wohlfarth model. The magnetic energy of this particle is composed of two terms, the uniaxial anisotropy and the Zeeman energy. Here, theta is the polar angle of the magnetization with respect to the easy axis, and theta h is the polar angle of the external magnetic field. Notice that we consider our particle has cylindrical symmetry, so that the azimuthal angle does not play any role here. Before starting our calculation, we will normalize the energy this way to obtain a tractable reduced energy. As a starter, let's look at the magnetic energy profile as a function of the angle theta in the absence of external magnetic field. I obtain this black curve. You see that this curve presents two minima, which correspond to the magnetization pointing either up or down. As long as no magnetic field is applied, these minima are equivalent and the magnetization can point in either direction. We have a bistable magnetic particle. For the sake of the demonstration, we assume the magnetization points up. Now, let's turn on the magnetic field and apply it against the magnetization direction. Then the energy profile gets distorted and the up direction is not stable anymore. Only the down direction is. Therefore, the magnetization must switch from up to down. What we would like to do is to obtain a general formula of the switching field for any direction of the magnetic field with respect to the anisotropy axis. So we look for a minimum of the magnetic energy, which means that we are looking for a value of theta that cancels both the first and second order derivatives of the energy. We obtain this system of equations that determines the angle of the magnetization for a given magnetic field direction. From that, we can deduce the switching field as a function of the field direction. This is Stoner-Wohlfarth formula. Now, what is the meaning of this formula? If I plot the switching field as a function of the magnetic field angle theta h, I obtain the famous Stoner-Wohlfarth asteroid. Let's see how I can use it to determine the magnetization switching behavior. In this discussion, the magnetic field is represented by a black arrow and the magnetization direction is represented by a red arrow. Let's first apply a small magnetic field along the easy axis. This is the same case as the one we discussed in the previous slide. Then the magnetization direction can be either up or down depending on its initial state. However, because there is no misalignment between the magnetization and the field, there is no torque, and the magnetization will remain in its initial state, up or down, until the magnetic field reaches the switching threshold. Once it reaches the threshold, the magnetization abruptly switches along the magnetic field direction. This abrupt reversal process leads to an hysteretic behavior. The figure on the right represents the projection of the magnetization along the external field as a function of the magnitude of the magnetic field. If the magnetic field is aligned along the easy axis as we just discussed, I obtain a square hysteresis, and the value of the field at which magnetization reversal occurs is set by the anisotropy field. Now, let us apply the magnetic field along the hard axis, so perpendicular to the rest position of the magnetization. Phenomenologically, you can guess that the magnetization direction will be tilted toward the magnetic field. Here comes an interesting property of Stoner-Wohlfarth asteroid. Let me draw straight lines passing by the tip of the black arrow and tangential to the asteroid. Then the direction of these lines determines the direction of the magnetization vector, depending on its initial direction. I can increase the field further and repeat this procedure until I reach the switching threshold. Here, the magnetic field is large enough to compensate the anisotropy and the magnetization points along the magnetic field. If I represent this behavior on the right graph, I obtain the blue curve. The magnetization progressively aligns on the magnetic field. Notice that this process is reversible and does not display any hysteresis. Finally, let me take an intermediate case. I apply the magnetization to 45 degrees. I can build the tangents to the asteroid as before, which gives me the two possible directions of the magnetization. The resulting hysteresis loop is reported on the right graph as the red curve. You see two remarkable features here. First, the switching occurs at a field much smaller than the anisotropy field. And second, the saturation occurs at much larger field. To conclude this discussion about Stoner-Wohlfarth model, one can wonder how realistic it is. Of course, if I take a very small magnetic particle with strong enough magnetic anisotropy, then I should obtain the Stoner-Wohlfarth asteroid. This was done by Wolfgang Wensdorfer by using 25 nanometer large cobalt nanoparticles. This figure demonstrates that such nanoparticles behave like the ideal Stoner-Wohlfarth model. Now, what happens to thin films? Here I show the study performed by Jonathan Sun's group at IBM. They used permalloy thin films with a thickness of 1 nanometer and nano-patterned into rectangular shapes with an aspect ratio from 2 to 5. What you can see is that a Stoner-Wohlfarth asteroid is obtained for the smallest system, but significant deviations are obtained for all the others. This means that for system size up to a couple of hundred of nanometers, the magnetization reverses almost coherently. But above that size, the reversal is not coherent anymore. An important mechanism that is completely overlooked by Stoner-Wohlfarth model is thermal fluctuations. This is a process we have already seen in the previous lecture on magnetic phase transitions, and we know that when these fluctuations are large enough, it can even quench the magnetic order. To understand how magnetic fluctuations influence the magnetization reversal, one can introduce an effective thermal field in the Landau-Lifshitz-Gilbert equation. The thermal field has a random direction and random magnitude, and its properties are given by the fluctuation dissipation theorem. Based on the theorem, the correlation function of the thermal field is a delta function in time and space, and its magnitude is proportional to both the temperature and the magnetic damping. With this thermal field in hand, one can determine the lifetime of a magnetic state as a function of the temperature. I am not going to enter into the details of the derivation, but let me just mention that one can obtain this lifetime through Fokker-Planck equation, as was done by Braun in his seminal paper. This treatment leads to an Arrhenius law, given here. Tau 0 is the attempt frequency, so the number of times the magnetization tries to get out of its rest position per second. K1V is the magnetic anisotropy energy of the particle. You see that it is proportional to the magnetic volume V, so the larger the particle, the larger the anisotropy energy, and the longer the lifetime. Then you have the zero temperature cohesive field, so the field at which the magnetization switches when there is no thermal fluctuations. And finally, the exponent here depends on the direction of the applied field and is rather phenomenological. The plus and minus sign depends on the field polarity. Let us test this formula by looking at experiments. First, it's not that easy to measure the lifetime itself, and it is often more convenient to measure the switching field. So let's transform this expression to obtain an expression of the switching field itself. Fine. Now, let me look at a first experiment down in the group of Olivier Frichard. Here, they measure the switching field of an array of self-assembled iron-silver nanostripes. Upon increasing the temperature, you see that the switching field decreases according to the Arrhenius law, as predicted by the model. Around 160 K, the switching field vanishes, and the nanostripes enter what is called the super-paramagnetic limit. In other words, thermal fluctuations are so strong that it costs almost nothing to orient the particle's magnetization. Notice an important point here. This super-paramagnetic transition is slightly different from the magnetic phase transitions we have seen in the previous lecture. The magnetization of individual nanostripes does not necessarily vanish. Its direction simply fluctuates because of thermal activation. Let me now consider another nice experiment by Nogas Givor and Ajip Anais. They consider 1 nanometer size core shell cobalt nanoparticles. The core is made of cobalt, and the shell is cobalt oxide. If you embed these very small nanoparticles in an alumina matrix, they are so small that their magnetization fluctuates down to very small temperatures, around 20 K. If you embed these nanoparticles in a cobalt oxide matrix, a dramatic change occurs. The cobalt oxide matrix is antiferromagnetic, so it exerts exchange bias on the cobalt nanoparticles. This exchange bias enhances the anisotropy energy of the nanoparticles and pushes the super-paramagnetic limit up to room temperature. I conclude this discussion by considering how magnetization dynamics itself is impacted by large thermal fluctuations. We have seen already that magnetization dynamics is usually described by the Landau-Lifshitz-Bloch equation. This equation works fine at zero temperature, and one can introduce a random thermal field to account for small fluctuations. These small fluctuations do not impact the magnitude of the magnetic vector itself. However, we know that when fluctuations are large enough, the saturation magnetization itself is reduced. How can we take this effect into account? In a recent series of works, Garanin proposed to modify the Landau-Lifshitz-Bloch equation to account for the thermal reduction of the magnitude of the magnetization vector. He proposed to add a new damping term that has this form and relaxes the component of the magnetization that is along the effective field. We end up with two magnetic damping parameters. The longitudinal one increases with the temperature, while the transverse one decreases with it. The expression of the effective field is a bit more complex as it acquires a new component proportional to the magnetization. Physically, it means that the longitudinal damping depends on the strength of the non-equilibrium magnetization itself. This contribution is proportional to the inverse of the susceptibility. The larger the deviation from equilibrium, the larger the longitudinal damping is. The validity of this approach has been tested by Oksana Shubikalo-Fesenko against atomistic simulations. In the atomistic simulations, a large ensemble of classical spins submitted to thermal fluctuations is considered. What the left figure shows is the way this classical ensemble of spins behave when they are taken away from the rest position and allowed to relax. When the temperature is below Curie temperature, not much happens. Since the thermal fluctuations are not too strong, the classical spins get reoriented coherently, and the overall magnitude of the magnetization remains almost constant during the process. Upon increasing the temperature, you can see that the overall magnitude of the magnetization experiences a dip at the beginning of the reorientation process, which means that the classical spins are strongly misaligned with each other. This is even clearer close to the Curie temperature, Above Curie temperature, the light blue curve shows that the overall magnitude of the magnetization can be reduced by 50% during the reorientation process. The right figures show the same simulations using the Landau-Lifshitz-Bloch equation. Here we are in the micromagnetic approximation, so you don't consider individual spins but rather a continuous vector field representing the collective magnetization. You see that very similar features are obtained, which indicates that the Landau-Lifshitz-Bloch equation can describe the longitudinal relaxation of the magnetization magnitude pretty well. We have seen a range of models that attempt to describe magnetization switching processes. The simplest one is Stoner-Wohlfarth Model that assumes a macrospin in a uniaxial anisotropy. This model works fine for small particles at zero temperature. If I turn on thermal fluctuation, then the magnetization switching will be thermally assisted following an Arrhenius law. I can go one step forward and introduce the thermal fluctuations directly into Landau-Lifshitz-Gilbert equation. I will obtain the Landau-Lifshitz-Bloch equation. That's all fine, but now the real question is, well, what happens in real life? How do real magnetic materials switch? To answer this question, let's look at an experiment. Here I will consider this work from Ackermann and co-workers. They studied the current-driven switching of a small magnetic film. The mechanism for switching is the spin transfer torque, something I haven't talked about so far and that I will discuss in a future lecture. That's not very important for now. What is important, though, is to look at the texture of the magnetization during the switching process. So Ackermann and co-workers took this magnetic spin valve, injected a current, and imaged the magnetic texture of the free ferromagnetic layer during the switching. Let's first consider the case of a thin ferromagnetic layer, 2 nanometers of permalloy. First, the magnetization points toward the right. Then it rotates coherently out of the plane. You can see that the arrows become very small because their in-plane component vanishes. And then something strange happens. The magnetization breaks into domains. You can even see a vortex forming momentarily. And finally, the magnetization is switched toward the left. Now we switch back. Again, the magnetization points coherently out of the plane. Some strange texture appears with a couple of vortices, and it switches. Good. Now let's increase the thickness of the free layer to 4 nanometers. Because it's thicker, I would expect some contribution from the dipolar field, and therefore more complex textures. Let's do it. I start with the magnetization pointing toward the right and commence the reversal process. Here I directly identify a vortex core pointing out of the plane. The vortex core is progressively expelled, and now we switch back again, and a vortex core of opposite polarity appears, pointing downwards. This one migrates across the sample and gets expelled. So what did I learn from this nice set of experiments? In thick enough samples, the magnetization reversal occurs through the emergence of magnetic texture and the migration of vortex cores, something that is completely disregarded in Stoner-Wohlfarth theory. Okay, so the previous slides told us that magnetic domain wall propagation is an important mechanism of magnetization reversal. What else? Well, there's another very important process in large-scale samples, which comes from the nucleation of reversed magnetic domains. Let's look at this picture taken by Stefania Pezzini's team. This picture shows the magnetic configuration of a trilayer of platinum, cobalt, alumina when submitted to an external magnetic field. The left picture shows the magnetic texture at small external magnetic field. In the dark region, the magnetization points downwards, and in the light gray region, the magnetization points upward. What you see is that the magnetization first reverses around impurities and defects Actually, the first reversal process is the nucleation of reverse magnetic domains. Then, when increasing the magnetic field, these reverse domains expand, which gives rise to full reversal, as shown in the right picture. In other words, in realistically large samples, magnetization reversal occurs through the cooperation between reverse domains nucleation and propagation. This sounds like a pretty complex process to model, but a nice theory was proposed by Fatuzzo in the context of ferroelectrics. Take a magnetic volume of area A and apply an external magnetic field. This field first nucleates reverse domains. This is a stochastic random process, so you could say that the number of nucleated domains is proportional to the number of nucleation sites and follows an exponential law. Here tau is the nucleation time. Well, that was easy. Now comes the propagation. The fraction of magnetic material that is reversed is proportional to the area covered by the expanding domains upon propagation. If I consider circular domains, I end up with this expression, where VDW is the domain wall velocity, and pi RC square is the initial domain area. Putting everything together, I obtain the total fractional area that is switched as a function of time. This formula was tested in the context of rare earth transition metal compounds by Labrune and coworkers. These two curves are experimental data, not simulations. You can actually parameterize your system as a function of the ratio k between the nucleation time tau and the domain wall expansion time VDW over RC. If domain wall nucleation dominates, k is very large, and you get the bottom curve. If domain wall propagation dominates, k is very small, and you get the top curve. To finish this discussion, let's go back to the hysteresis that we first discussed in the context of Stoner-Wohlfarth Model. As we have seen, many complex processes contribute to the magnetization reversal in realistic samples. Thermally activated Stoner-Wohlfarth model consistently apply to small magnetic systems with large anisotropy. In larger samples though, even if the external field is aligned along the z-axis, there's little chance I'm going to observe square hysteresis. I rather observe a rounded hysteresis like that. In this hysteresis, I can define the saturation magnetization as the value of the magnetization at very large fields, and the remnant magnetization as the value of the magnetization at zero field. The coercive field is the field at which the magnetization switches, and may not be equal to the anisotropy field. The area of the magnetic loop is equal to the energy loss during the reversal process. To test whether the reversal is dominated by nucleation or propagation, one technique consists in first demagnetizing the magnetic sample by creating as many magnetic domains as possible, and zero overall magnetization. This can be done by sweeping the magnetic field back and forth along unsaturated states in the hysteresis. Once the sample is demagnetized, applying a large external field will remagnetize the sample, and the way it remagnetizes it indicates whether the switching process is dominated by propagation or nucleation. We conclude this lecture by addressing a second class of dynamical effects, the ferromagnetic resonance. I go back to the Landau-Lifshitz-Bloch equation that is composed of a precession term and a damping term. If I consider a magnetization vector and I apply a static magnetic field, the field torque will induce a precession of the magnetization around the magnetic field direction. Therefore, in the absence of magnetic damping, the magnetization vector precesses indefinitely around the applied static field. Now, if I turn on the magnetic damping, Then the precessing magnetization will progressively realign itself along the static field. That happens because the magnetic energy is relaxed. So if I can find a way to continuously pump energy in my system, the magnetization would precess continuously even in the presence of magnetic damping. I can do that by applying a small oscillatory field perpendicular to the static field. When the frequency of the oscillatory field matches the precession frequency of the magnetization, I obtain a resonance, and the magnetic damping is fully compensated. To see how it works, let's consider the following magnetic energy, composed of anisotropy terms and the external magnetic field, along both the x and z direction. Using the Landau-Lifshitz-Bloch equation, I obtain three coupled equations in which nx, ny, and nz are the magnetic anisotropy fields. To treat this problem, I will consider that the applied oscillatory field is small and that the magnetic oscillation around the static field is also small. The static field is along z, so that magnetization is mostly along z, and I can linearize my set of equations by neglecting the terms that involve higher order corrections. This leads to the coupled equations for the magnetization component that are perpendicular to the static field. Fine. Now, how do we solve that? Since we have an oscillator, we will take the Fourier transform of these two equations and we can directly compute the susceptibility of the magnetic system under the oscillatory field Hx. The susceptibility adopts a Lorentzian shape with resonance frequency omega 0 and broadening gamma that is directly proportional to the magnetic damping. These two figures outline the characteristic features of ferromagnetic resonance. First, the norm of the susceptibility shows this characteristic Lorentzian shape, whose full width at half maximum is proportional to the damping coefficient. The magnitude of the susceptibility at resonance is inversely proportional to the damping. So, the larger the damping, the broader the peak. The resonance frequency can be tuned by applying an external field, following the famous Kittel law. Of course, you can imagine that magnetization reversal and ferromagnetic resonance are of central interest for magnetism. But they have received renewed momentum in the past 20 years with the discovery of the spin transfer torque. As I already mentioned, spin transfer torque is a mechanism by which a current of spin-polarized electrons transfers spin angular momentum to the local magnetization and thereby exerts a torque on it. Therefore, one can induce magnetization reversal by simply injecting a spin-polarized current into a small magnet. The picture on the left is just one of many examples of such a switching. Controlling the magnetization direction using electrical currents can lead to many nice applications, such as the magnetic random access memories. One can also induce magnetic resonance by injecting spin-polarized currents. This way, one can obtain electrically controllable radio frequency oscillators. We have seen that when we take a piece of magnetic material and submit it to an external magnetic field, we can induce magnetization reversal or high-frequency resonance. Most of the models we have been discussing so far assume the macrospin approximation, which means that they assume that all the magnetic moments are aligned along each other. In other words, the exchange is large enough. Well, we have also seen that this is not always true. When the magnetic materials become big enough, let's say 100 nanometers and above, then the dipolar coupling takes over, tries to minimize the magnetic flux, and creates magnetic domains. Now, the next lecture will focus on the nature of these magnetic domains and will particularly pay attention to the boundary between two successive domains, which are called the magnetic domain walls. Let's move on.